Hello everyone. In today's lecture of solid state chemistry, it is having an immense importance because the subject area that are going to be discussed is three basic laws of crystallography and symmetry elements of crystal. These are very vital things. Okay, so let's start with the three basic laws of crystallography. There are three basic laws of crystallography. So the firstly, the Steno's law of constancy of interfacial angles. The second one is the Haüy's law of rational intercepts, and finally the third one is the law of constancy of symmetry. So let's begin with Steno's law of constancy of interfacial angles. What does it say? This says that the angles between the corresponding faces on various crystals of the same substance are constant. What does it mean? It means that the crystal faces may develop unequally due to different rate of deposition of atoms or ions on the different faces, leading to various shapes of crystals. But the angle of intersection of two corresponding faces will always be the same for any crystal of the same substance. That means the faces, the crystal faces, they intersect with each other, then an angle is formed, and that angle should be constant, whatever be the external shape. Okay, let's elaborate with the diagram. Suppose these two are two hexagons, but this is this is a regular hexagon and this is an irregular hexagon. All the side lengths of this regular hexagon are same, whereas this is here the side lengths are not same, but the interfacial angles are same. Okay, it is clear, easily you can visualize that the angles are same. Okay, so here their shapes are different, but the interfacial angles are same. So this is about the first law. So now one question might arise, that the sodium chloride crystallizes as a cube when it is obtained from an aqueous solution, whereas it is the octahedra shape is obtained when it is taken from urea solution. Okay, so the question is what? Why does sodium chloride crystallize as cubes from aqueous solution and as octahedra from urea solution? Do they have different crystal structures? The answer is no, they do not have different crystal structures. They have the same crystal structures, but their rate of deposition of the atoms are different due to being present in different solutions or mediums or media. Okay, so let us find out the answer. The answer should be written like this: sodium chloride crystallizes as, here an S should be added. Sodium chloride crystallizes as cubes from aqueous solution and as octahedra from urea solution due to different rate of deposition of the ions on the different faces. Okay, the Na plus ion and Cl minus ion. So according to Steno's law of constancy of interfacial angles, what does the law say? The law says that the angles between the corresponding faces on various crystals of the same substance are constant. Therefore, the external form or habit may be different, but the angles of intersection between two corresponding faces will always be the same. Here's the picture. Look, the external shape is cubic, whereas the internal shape is octahedral, but the crystal structure is same, isn't it? Sodium, 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 chloride, 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 chloride. Okay, so when this shape is externally repeated, then it will look like an octahedron, whereas when this shape is repeated externally, then it will look like a cube, but the position of the corresponding position of the ions are same. The respective position of the ions are same. Now, how you draw this picture? It is very easy to draw. Apparently it looks a little bit difficult, but it is very easy to draw. First, draw a cube. Okay, two squares and join the apices. Then take the face centers as a dot. Then join these dots. Okay, first draw this parallelogram, then draw a straight line from this top point and also from the bottom point. Then the octahedron is obtained. Okay, Now these dotted lines are actually the facial diagonals of each faces of the cubes. So this is very easy to draw. Now let's go to the second law, which is the Haüy's law of rational intercepts. What does it say? It has two forms. Okay, one of the forms is the regular external form of crystals is a reflection of the inner regular order of the arrangement of the building units. Or there is another form, which is for any crystalline studies there is a set of axes in terms of which all naturally occurring faces have reciprocal intercepts proportional to small integers HKL. So what is that? This is nothing but the definition of unit cell, isn't it? Look at the importance of this law. The importance of the law is, this law is the foundation of crystallography and the basis of crystal system. And secondly, the idea was confirmed more than 100 years later by means of X-ray diffraction studies. Okay, this was simply an idea, but later in the laboratory, by doing practicals, okay, it was confirmed, but it was done 100 years later. Now this law is interpreted as what we are going to give as points here. These are nothing but the definition of a unit cell. Look, what is it? Firstly, a crystal is made up of innumerable number of smaller crystals. Okay, if a crystal is suitably and continuously divided, then smaller and smaller crystals being replica of each other would be obtained, definitely. And finally, the smallest possible crystal that cannot be further divided is the building unit of the crystal, which is known as the unit cell, isn't it? So this is ultimately the definition of unit cell. That is why this second law is very important. But the third law is the most important one, because the symmetry elements are taken into consideration here. This law says that the crystals have a set of symmetry elements such as center of symmetry, plane of symmetry and axis of symmetry. So let us move on to the second part of this lecture, which are the symmetry elements of a crystal. Okay, so let's start with the center of symmetry, which is symbolized as small letter I. So if every face of a crystal has another identical face at an equal distance from a central point, then this point is called the center of symmetry, symbolized as I. Okay, and what is the feature? The feature is that each and every out of the 7 crystal systems has one center of symmetry. So we have 7 crystal systems: cube, tetragon, trigonal, then orthorhombic, monoclinic, triclinic, hexagonal. Okay, so all these 7 crystal systems, each and every one must have a center of symmetry. Okay, and I. Here is the picture. This is the center of symmetry. So this point is repeated here. This point is repeated here. If you trim this portion with like a triangle, and also opposite portion like a triangle, like this picture here, then also you will get the same center of symmetry. So this is center of symmetry. Now plane of symmetry, which is symbolized as sigma. When a crystal is divided by an imaginary plane into 2 halves such that one is the mirror image of the other, then that imaginary plane is called the plane of symmetry, symbolized as sigma. That means, just imagine a plane and divide the crystal or divide the unit cell into 2 equal halves. Then if you find that one half is the replica of another half, then that particular plane is the plane of symmetry. And you will see that a cube has 9 planes of symmetry. Okay, 9 different planes of symmetry. It is not more than 9, not less than 9. It is exactly 9. Okay, so here are the pictures of the 9 planes of symmetry. Okay, and finally the axis of symmetry, which is symbolized as small letter n. So a crystal possesses a line of symmetry when it is possible to draw an imaginary line through the center of crystal and then revolve the crystal about this line through 360 in such a way that the crystal appears unchanged more than once. This line is called the axis of symmetry, denoted as n, and this is also called the order of rotation. Okay. Sometimes it is also called fold. The fold term is used. Suppose you are repeating the structure by rotating through an axis 4 times. Okay, then it is a 4-fold axis. If you are you are undergoing the operation by 2 times, then it is 2-fold axis. That means in every 180-degree rotation, the same structure is repeated. Okay, then it's a 2-fold axis. If at every 120-degree rotation the same structure is obtained, then it is a 3-fold axis. Similarly, for 90 degree it is a 4-fold axis. Okay, so have a glance to a cube. You will find that cubes has all these 3 rotation axis of symmetry: 2-fold, 3-fold and 4-fold. And if you try to count them, you will find that the number of 2-fold axis of symmetry are 6 for a cube. 3-fold axis of symmetry are 4, and 4-fold axis of symmetry are 3. So as a whole, 3 plus 4 plus 6, that is 13 number of axis of symmetry for a cube. So a cube has 1 center of symmetry, 9 planes of symmetry, and 13 axis of symmetry. Okay, in total it has 23 elements of symmetry for a cube particularly. We shall try to find for the other crystal systems also. Okay, and here is the question regarding this. Find out the symmetry elements of orthorhombic, tetragonal, monoclinic and triclinic crystal systems. Okay, so let's begin with number 1, which is orthorhombic. So here is the description. You will try to find it. You try to imagine also. Center of symmetry, definitely it is common. 1 plane of symmetry, there are 3 planes of symmetry. Okay, and out of the 4 types of rotation axis, 2, 3, 4 and 6-fold, only 2-fold axis of symmetry is available in case of an orthorhombic, and 3-fold, 4-fold, 6-fold are not possible. Okay, so this is the center of symmetry, and these 3 are the axes, and these 3 are the different planes. Okay, for an orthorhombic crystal system. After orthorhombic, we move on to tetragonal. Tetragonal has only has center of symmetry. This is common, and 5 planes of symmetry. Okay, out of which it has 2 sets. One has 3, another set has 2. Okay, we'll see in the picture. And out of the 4 types of axis of symmetry, it has 4 number of 2-fold axis and only 1 4-fold axis. Here's the picture. Okay, this is a tetragonal structure, and look, this is the center of symmetry as usual. Now 2 sets of plane of symmetry. Okay, one is just here. This is one plane of symmetry. Okay, this is another plane of symmetry. So this is another, and the third one is this one. So this is out of the 3 sets, and out of the 2 sets, this along the diagonals. Okay, volume diagonals. It becomes a prism when you cut like this, and this also is a plane of symmetry. Okay, now try to count the axis of symmetry. 4-fold axis. This is the 4-fold axis. Okay, this is the 4-fold axis. That means in every 90-degree rotation, the same structure is repeated, and these are the 2-fold axis. Okay, this is 2-fold axis number 1, This is 2 4 axis number 2, which is actually the perpendicular of each vertical face. Now the perpendicular of the edge, okay, at 45 degree angle. From this angle is 45 degree, and I'm sorry, this is not 45 degree, 90 plus 45, that means 135 degree, sorry, at 135 degree and 135 degree, okay. And with respect to this line, this is 90 degree, that means this angle is 90 degree. This is one, and at this corner this is also another one. This angle is 90 degree, this angle is 90 degree, whereas this angle is 135 degree, okay. So these are the 4 axes of symmetry for a tetragonal crystal system. After tetragonal, we move up to monoclinic. Monoclinic has 1 center of symmetry and only 2 fold axes of symmetry. It does not have any plane of symmetry. So this is a monoclinic system. After monoclinic, we have the triclinic system. A triclinic system has only a center of symmetry, so no need to draw a picture for a triclinic system, and nothing is there. So these are the answers. Now next question is, only 2, 3, 4 and 6 fold axes of symmetry are possible, okay, but why not 5, 7 or higher order are possible? Why not 8 fold axis? Why not 9 fold axis, or 5 fold or 7 fold axis? There are 2 types of answers, okay. One answer is logical. What is the logic? The logic is, if you let's see the diagram first, then the description would be more easier to understand. Look, with the triangles, you're trying to fill up a plane, no gap is obtained, okay, all the gaps are filled up. Take a square, there is no gap. Take a hexagon, there is no gap. But if you take a regular pentagon, a regular heptagon, or a regular octagon, you will find either there is some gap or there is some overlapping. For a pentagon or for an octagon, there are gaps. This is the gap, okay, this is the gap, this is the gap, this is the gap. Or for a heptagon, that means 7, having 7 edges, 7 sides, this is some overlapping, okay, this is some overlapping area. So logically, this is not, these 3 types, 5, 7 or 8 are not possible, but 3, 4, 6, even 2 are possible, but 2 cannot be diagrammatically here shown, okay, but logically you can describe it. How? If we use either a square or an equilateral triangle or a hexagon to cover up some place by repeating them again and again, we can arrange them such a way that there will be no gap between them. So these kinds of symmetry with 2, 3, 4 or 6 fold rotation axes are possible. Now if we take a uniform pentagon or a hexagon or an octagon and try to cover some plane area by repeating the polygon many times, it is not possible to find an arrangement where there will be no gaps or no overlappings. Therefore 5, 7, 8 or higher order symmetry axes are not possible in crystals. So this is one way of answering this question. There is a more mathematical approach, okay, where you can prove this geometrically. So let the lattice have n-fold rotation symmetry, okay. N-fold means 360 by n. The angle is 360 by n. So this angle is alpha, this is 360 by n, okay. Now this is the symmetry element, okay. Now if you rotate this by alpha angle, this point, A dash point, moves to B dash point, okay. Now what is the edge length? The edge length is from this point to this point, this point to this point, and this point to this point. This is A, okay, the unit cell length. This is. Now after undergoing the operation, okay, after performing the operation, this A dash point moves to B dash point, okay, then this distance should also be A to B, A dash to B dash, should also be some integral multiple of A. That means it should be NA or MA. Okay, now N is the what I say is the axis of rotation. Okay, n-fold axis of rotation. So the integral multiple should be taken as M. So let's start. Let the lattice have n-fold rotational symmetry about the axis passing through the lattice point and perpendicular to the plane of the paper. By performing a rotation of angle alpha, which is actually equal to twice pi by n, that means 360 degree by n, we can get back the same lattice, isn't it? Yes. So in the figure, A dash and B dash are the lattice point as A and B, as A and B. Isn't it? This point is A, this point is B, and the operational points are A dash and B dash. Okay, thus we can write A dash B dash must be equal to M into AB, where M is an integer. Then AB is what? AB is nothing but edge length small letter a. Okay, so the condition is A dash B dash, this distance is an integral multiple of capital AB, that is small letter a. Okay, so in place of capital AB we have to write in small letter a. So here in the right hand side we have written this M into A, small letter a. And what we have written in the left hand side, we have split this line into three parts. One is A dash to X, another is X to Y, and the third one is Y to B dash. Okay, A dash X, XY, and Y B dash. Now what is the value of A dash X? If this angle is alpha, then this angle is also alpha, and then this is nothing but, this is the same edge length, isn't it? So this is A cos alpha. Similarly, this is also A cos alpha. So A cos alpha plus A cos alpha, because XY is A, this XY is also A, is equal to AB, that means small letter a. So A dash X is A cos alpha, XY is A, and Y B dash is also A cos alpha, and this is equal to MA. Or solving, we can get cos alpha equals to M minus 1 by 2. So this is equation number 1. Now as the value of cos alpha, the maximum value of cos alpha is plus 1 and the minimum value of cos alpha is minus 1. Now let us put different values of the integral multiple M. Okay, M may be started from 0. Okay, so randomly we just put the values. If we put M equal to 0, then cos alpha is minus 0.5. And if cos alpha is minus 0.5 and M is 0, then alpha is 120 degree. 120 degree means threefold axis. So threefold axis is possible. Now for M equal to 1, you will get that cos alpha equal to 0. So cos alpha 0 means what? Alpha equal to 90 degree. 90 degree means it is fourfold. Putting the value of M equals to 2. Okay, for M equals to 2, in equation 1 we will find that cos alpha is plus half, that is 0.5. So plus half means 60 degree, isn't it? And 60 degree means 360 by 60, that means 6-fold axis of symmetry. By putting M equals to 3, you will find that the value of cos alpha is 1. 1 means cos alpha is 0 degree or 360 degree. Okay, so this is actually one-fold axis, that is the identity. One-fold axis is actually the identity, because after a complete rotation of 360 degree, the crystal comes back to its own position again. So this is the identity. Okay, so this is also actually validated with the help of this value of M equals to 3, which results in cos alpha equals to 1, that results in alpha equals to 360 degree. Okay, that means the rotation axis is 360 degree. Now finally, if M equals to minus 1, then cos alpha equal to minus 1, and then that angle of rotation is 180 degree, that is two-fold axis. So this is more appropriate proof. So from this table we can conclude that 1, 2, 3, 4 and 6-fold symmetry axis of our crystal can exist, but no but 5 or 7 or higher order symmetry axes are not possible. Okay. So that's all for today. Thank you. Have a nice day.